Okay, in this tutorial video we are going to consider a topic very near and dear to any measurement scientist's heart, and that is properties of measurements, precision, and accuracy. I'm going to rate this particular topic importance of around 3 out of 4 stars. It's not uncommon to see a question that's based in these ideas on standardized type exams or on semester type exams. The types of questions you would face would require that you understand the concepts that we're going to talk about and apply them in sort of a higher order cognitive way. So we're going to review the basic concepts. Whenever you go into lab and make a measurement, that measurement will have varying degrees of precision or accuracy. Now, what do we mean by precision or accuracy? Well, so the textbook definition, if you will, of precision is a measure of the reproducibility of a measurement result. If you do the experiment 5 times, do you get the same answer over and over and over again, or close to the same answer? And the degree to which that occurs is related to your precision. I would argue that precision is a little bit more complicated of an idea than just the reproducibility. Of course, the reproducibility does play a role in precision, but I like to think of precision as the analyst's ability to distinguish between 2 closely spaced measurements. Can you distinguish between 1 millimeter and 2 millimeters? Do you have a precise enough device to do that? And of course, a ruler would be easy enough to do that. But if you just had a plastic ruler, could you tell the difference between 120 micrometers and 121 micrometers from a ruler that you might find in your book bag? Probably not, because it lacks the precision. Okay, so the ability to measure between 2 closely spaced variables is, to me, what precision is all about. Okay, and that of course has to do with reproducibility in terms of replicate chemical analysis. More on that later. But accuracy is a completely different concept. It's how close a measured result is to the true value. If you make a measurement, is your measurement accurate? Is it reflective of that true value, or is it completely wrong? In some cases, you might have a procedure there's an error in it, maybe a wrong reagent or a bad reagent, and you'll always get the wrong answer. But that happens in a reproducible way, so your precision might be very good, but your accuracy is horrible. To demonstrate these concepts, oftentimes people show little targets. So I brought into this just to kind of review in case you're struggling with precision and accuracy. This is a target illustrating pretty good precision. The shooter's placements are all within the same region of the target over and over and over again. However, they're off the center, so it's not very accurate. Of course, the goal is to hit the center. So precise, but not accurate. On the other hand, we might have this placement of shots. Boy, this shooter is neither accurate nor precise. Scattered all about the target. None are really at the center except for this one, which may have just kind of happened randomly by random chance. But in the last case, we've got this shooter, which is both precise and accurate. All their shot placements are very close to the center. That's of course what we'd like to achieve, to have very, very high performance in our target shooting. So measurements, just like in target shooting, can be accurate and they can be precise. They can be both accurate and precise. Given technique might always give the wrong result, but it might do that over and over and over again. In that case, it's precise, but it's not accurate. So chemists need a couple things. We need to have a quantitative way to describe just how accurate or precise a result is. We also need some techniques that we can detect whether or not our method is accurate. Okay, so it's not good enough just to have these targets. I mean, that works for target shooting, and the visual is very useful because we understand what the goal is here. We understand what precise is, what's accurate. But you know, if we're in lab with chemicals and reagents and making measurements, you know, we don't have these targets. We don't have the same visual. So we need to have quantitative indicators of our accuracy and precision, and that's what's important to us. Okay. So let's talk a little bit more about accuracy and precision now. And to help us do this, what I'd like to do is introduce different types of error in our analysis. Okay? And these types of error basically are directly reflected, or they directly reflect the precision and the accuracy with which our measurements can be made. So the first thing that you need to know any measurement that you make in lab or that the data is reported to you is subject to error. Lots of things can potentially go wrong, leading to imprecision or just outright inaccuracy of our data. And you need to accept that, okay? Because it's always the case. You cannot completely eliminate error. And that's important for you to know. There are two different types of error, if we study error, that can come up. There's the so-called random error. That's called indeterminate error. That's a key term that you'll want to know. Okay? Indeterminate error is synonymous with random error. The second type of error is determinate or systematic error. Fundamentally different types of error. Okay? The random error is always present. Okay? Random error is always present. You can never completely eliminate it. This is that sort of random high, random low type of error. Sometimes the measurement's a little high, sometimes it's a little bit low. The beauty of the random error is there's a tendency to cancel each other out if you make a large number of measurements. Okay, so oftentimes in your chemistry lab, your instructor will want you to make maybe even 10 measurements, right? And you kind of secretly go back to your lab bench and a little bit disappointed and maybe curse them under your breath or something. But the reason for doing that is if you make a large number of replicate analysis, these random errors tend to cancel each other out. Okay, so what does the random error, or how does the random error influence a histogram or a distribution of acquired data? Okay. Well, if you had very, very, very low random error, your distribution of data might look something like this, okay? In other words, this is the frequency of measurement versus the value that you measured. Just about every time you get the same exact result. Sometimes you're a little bit higher than the most frequent value. Sometimes you're a little bit lower than the most frequent value. But boy, most of the time you are very, very close to the same measured value over and over and over again. Again, this is frequency with which a value is measured as a function of the value measured. Now, if your analysis has higher random error, but no systematic error, data would look something like this in a scatter plot, okay? The breadth or the width of the distribution would be wider in the case of more random error. Okay? And that will be reflected in things like the standard deviation. We'll get into that here in a little bit, but the breadth of the measurement becomes wider. The other type of error is determinate or systematic error. These again are synonyms. This is the type of error that introduces a bias into your result. It makes your answer wrong. Remember we said in random error, if you take enough samples of data, if you do enough replicates, they tend to cancel each other out because sometimes they're a little high, sometimes they're a little low, and there's a sort of cancellation effect. And usually not completely, but there is a tendency towards the mean. Systematic error, if you have systematic or determinate error in your analysis, there is something that's just wrong with your method. Maybe there's a broken device, a bad chemical, operator error, whatever it is. Systematic error, something is wrong. And this introduces bias. And bias basically makes your result incorrect. So if I was to come up with the same plot, frequency of measurement versus value measured, for an analysis with no systematic error, maybe my distribution of data looks like this. So no systematic error. Okay? And there's my mean, and that means correct. If I introduce systematic error, my distribution will be shifted, either higher or lower. I'm going to draw it lower. But there's a shift. in the value that's measured to a different number. Again, I drew it lower. It could be just as easily higher. Okay, just running out of space over on the right. But I'm shifting my distribution away from where it should be if there's no systematic error. So this is with systematic error. So the key point is my measurements, my measured values are now different. They're incorrect. Okay. So determinate error, systematic error, usually results from faulty equipment, operator error, some sort of problem with the procedure. And if you identify that problem and eliminate it, you may be able to eliminate or reduce the systematic error and get the right answer. But if systematic error is present, you'll never get the right answer because your analysis is always going to be wrong. Okay? So random errors affect the breadth of the distribution of data. Systematic errors make your answer inaccurate. Systematic errors make your answer inaccurate, and you may have guessed it, random errors make your analysis more or less, what? Imprecise. Okay, so random errors are sort of the domain of imprecision. Systematic errors sort of the domain of accuracy. Now, analysts have a little bit of a problem when they're considering their measurements. The first problem is when you're considering a data set, how in the world do you know whether it's accurate? How do you know whether systematic error is present? Because you just go do your experiment. You may get good, what appears to be good data. However, it could be full of systematic error, determinate error. So how do you tell that that's there? Okay, there's a couple things that you can do. You can run a blank. It's a key term. A blank is everything in the sample the sample that contains everything except the assayed substance. It doesn't contain your analyte. And of course, if you run a blank, you should get 0 for your signal or your response. If you don't, that could be indicative that there's some sort of systematic error present. Okay, something else in the sample matrix might be interfering. You might conduct an independent analysis. You could analyze your sample using another different accepted technique. Do your results compare well? Are they the same? Does method 1 and method 2 produce the same results? If that's the case, you gain confidence that your analysis is without determinate error. And lastly, you might use standard reference materials. These standard reference materials contain basically known amounts of the species to be assayed or determined. You can obtain these standard reference materials from agencies like NIST, for instance. They have over 900 standards and always growing. You can purchase a standard reference material, and this is basically a substance or a material like maybe blood or urban dust or something of the sort that's been analyzed by many different methods over the years. So to a high degree of certainty, we know what's in these samples and we know the concentrations of the substances. Analyze a reference material. If your method produces results consistent with what's known to be present in that material, you gain confidence in your method, okay, being accurate. If you get the correct result, you gain confidence. If your method gives you the incorrect result, you know that there might be systematic error, systematic bias that you need to identify and hopefully remove. So these are some things that we can do to determine whether our measurement is accurate. But even if we do that, how can we describe the precision and the accuracy of measurements in quantitative terms? We'd like to be able to do that. There are some common indices of both accuracy and precision that we should talk about. Let me remove this, it's in the way. We want to talk about accuracy of a result. We can do that in quantitative terms by absolute error or relative error. Okay? The absolute error is pretty easy to calculate. Okay? E is the absolute error. It's set equal to being equal to x sub I minus x sub true. X sub I is simply the measured data set average, and we're going to subtract x sub true, which is the true value. To be honest, this is oftentimes given as an absolute value as well. A little bit flexible. I mean, you could do it either way, I guess, but oftentimes you might report that as an absolute value, so it's not negative. It's just the difference between what you measure and the true result. And that's absolute error. Alternatively, we can describe a relative error. You can describe it as parts per 100 error or parts per 1,000 error. Parts per 100 error is going to be pretty familiar to you, okay? We typically call that percent error. If you've taken a lab class, you've probably had to calculate that before. It's a relative error because relative errors are normalized back to the mean of the data set. To compute per percent error, all you have to do is take the data set average mean, subtract the true value, divide it by the true value, take the absolute value, multiply by 100 to express it as a percent. If you want to compute parts per 1,000 error, you do the same calculation but multiply by 1,000 at the end, okay? To discuss the error in terms of part per 1,000 instead of parts per 100. These are both relative errors, okay? Because what it really does is it finds the difference between what you measure and the true value. It normalizes it back to the true or accepted value, okay? So it expresses your error as a percent of the true value, okay? As a ratio back to that true value. And that's what makes it a relative error. Oftentimes analysts like to use the relative error because it does do that ratioing back to the true value. Absolute error, you can never truly be completely sure how good a job you've done. I mean, if I tell you the error was 1 millimeter, am I measuring the thickness of a human hair or the distance to the sun? Right? In one case it would be very good relative error, the other it would be very poor relative error. That's why we like to oftentimes ratio back to the true or accepted value when reporting our relative errors. So that's how we can describe accuracy. What about precision? To discuss the precision of a quantitative result, we have a couple different variables that we can use. We might discuss the precision as a mean deviation from the mean, MDFM. We might call it a range, just high minus low. Standard deviation, S, is a very popular way to discuss the precision of our result. We'll talk about how to calculate standard deviation and relative standard deviation in a separate video. It's very, very important for your quantitative analysis class to be able to calculate both of these. It's almost a requirement for successful completion of the class. So there are other videos to help you with that if you struggle. But there's standard deviation and also something called relative standard deviation. We'll consider how to compute these in a separate video. Hope you've enjoyed this brief review of measurement accuracy and precision, and we will see you soon.